Okay, so we will be discussing the first four problems. So let's go through the first problem, which was twin permutation. So in this, as I said you that you are given a permutation A of length n, and you have to find any permutation B of length n such that this condition holds, right? That is A1 plus B1 lesser than or equal to A2 plus B2, so on and so up to An plus Bn. Okay, and it can be proven that such a permutation B always exists. Okay, just a quick reminder that in case you feel any doubt, you can just unmute yourself and ask directly, right? Or if you feel like there is some lag or net issue. Okay, so let's see what can be done for this. So basically for problem A, what you are given is that you are given an array A1, A2, A3, so on and so up to An. So this is in fact a permutation, right? You have to construct another permutation B, B1, B2, so on and so up to Bn, such that A1 plus B1 lesser than or equal to A2 plus B2, so on and so up to An plus Bn. Okay, so if you consider a very simple permutation like 1, 2, 3, 4, so on and so up to n, so you can just replicate this array 1, 2, 3, 4, so on and so up to n. If this is your permutation A, so your permutation B can be simply written like this. So in this case, you can quickly see that 1 plus 1, 2, 2 plus 2, 4, 3 plus 3, 6, so on and so up to 2n. So obviously these forms increasing sequence. Okay, but let us try to see what happens if some permutation is given which forms a very worst case. So let's say if you are given permutation like n minus 1, so on and so up to 1. So this is a strictly decreasing permutation. Okay, so in this case what can be done? So if you write a sequence like this, that is 1, 2, 3, and up to n, and if you try to now find the value of ai plus bi, so this becomes n plus 1, this becomes n plus 1, here it was n minus 2, so it becomes n plus 1, and at the end you will see that everything has become equal to n plus 1, and obviously it holds this constraint because everything is equal, right? So indeed you will find that you can always find a permutation b such that ai plus bi is equal to n plus 1. So like if you are given permutation of 5 integers like this, okay, so in this case n is 5, so just replace in your b array, your bi values will be nothing but n plus 1 minus the value of ai. Okay, so for example in this case n plus 1 is 6, 6 minus 4 is 2, this becomes 5, this is 1, this is 4, and this becomes 3. So obviously you can say this is again a permutation and the value of ai plus bi remains equal, remains constant, that is n plus 1. Okay, so this was a very simple problem that all you have to do is to form your array B such that the ith element of B array is n plus 1 minus ai. In that case, the value ai plus bi becomes constant, that is equal to n plus 1. So definitely in that case, the constraint that a1 plus b1 greater than, lesser than or equal to this one holds because everything is instead equal. Okay.
Can you explain this part again? N plus 1 minus AI.
Can
Sir,
you repeat, like your voice was breaking?
Yeah,
hello,
N,
am I
N
audible?
plus 1 minus AI part.
Uh, you were giving me a case, right?
No, you have written
Uh,
N plus 1 minus AI here. So how
yes.
do we...
Okay. See, what I want is that you are given your array like let's say A1, A2, A3, A4. Let's say this is a permutation of 4 numbers, right? Now you have to form a sequence like B1, B2, B3, B4. Again, this should be a permutation. What I'm trying to say is that let's say the value of AI plus BI becomes a constant number. Let's say that becomes equal to n plus 1. So in that case, what your BI value will be? BI will be nothing but n plus 1 minus AI, right?
Okay.
Okay, so that's why your B array is formed like this, that the ith element is equal to n plus 1 minus AI. And obviously, this will always be a number within the range 1 to n, because if AI is very small, let's say 1, so in that case, you get your n plus 1 minus AI as n. And if AI is very large, let's say n, in that case, you get 1. So obviously, this value will always be in range 1 to n, and since ai is distinct, so this b array will always be distinct, hence it will be a permutation. Is this clear to everyone?
Sir, why only n plus 1 means what's the logic? How did you reach to the conclusion that
Okay.
the permutations will be formed from n plus 1 minus the sum element?
Mhm. Okay, so you are saying why not the sum of ai plus bi is something like n plus 2? Why only n plus 1, right?
Yeah, yeah.
Okay, so let us consider a sequence. So that's why I told you, like, let's try to see whether we can do it if very weird permutation is given. Let's say the permutation of 5 numbers like this: 4, 5, 4, 3, 2, 1. Okay, so that is strictly decreasing sequence, right? That is n, n minus 1, so on and so up to. Okay, so let us say if you try to put in the place of n, if you try to put n in the place of n, let's try to put 2. So your sum should be constant equal to n plus 2. Now in the right of it there must be somewhere 1. Okay, so what should be then here? It should be n plus 1, but n plus 1, like, you can't put, it's a permutation of 1 to n numbers. Okay, so if you put here anything which is greater than 1, okay, so that your sum becomes n plus 2, n plus 3. So in that case, uh, in the bottom of 1 you will have to write like n plus something which is at least 1. So like if in case of putting here 3, you will have to write here n plus 2, but this violates the permutation constraint. That's why best is to put 1 over here, so that in the worst case you can write n over 1. Did you get it now?
Yes, sir, yes, sir.
Okay. Any other doubts?
We were just given that we need AI plus BI strictly lesser than AI plus 1 plus BI plus, like strictly lesser.
No, I don't think so. Let me check.
No, we are not given in this question, but what if we were given? That's what I'm asking.
Okay, you are saying what if? So see, in that case, it's all dependent on your constraint, like in your input permutation. It won't be always possible to form such a permutation, because as you can clearly see, in this case only, if your permutation is a strictly decreasing sequence, let's say like this, n, n minus 1, n minus 2, like up to 1. So in that case, even if you put 1 over here, even if you put 1 over here, okay, so that this number formed is the smallest one, even if it is n plus 1. So below 1 you will have to like put in the worst case n. Below n you can only put n in the worst case. So in that case n plus 1 will come. So this n plus 1 is not strictly smaller than this n plus 1. So in that case it
We
the
cannot
answer
form
won't
a
exist.
permutation. Yeah,
Yeah, yeah, so in that case it would be all input dependent.
yeah, got, got.
Okay, yeah. So if it is clear, let's head towards its solution or submission. Okay, so it's a very basic solution, like just input your size of the array, take your input, and then for each position, like the value of bi, that will be nothing but n plus 1 minus bi, n plus 1 minus ai. Okay, so now let us move to the next problem, which was problem b, that is array merging. So in this problem, you are given two arrays A and B, and both of are length n. Okay, and you have to merge these arrays, forming another array C of length 2n. And then you have to find the maximum length of a subarray consisting of equal values across all arrays C's that could be obtained. Okay, so basically you are given two arrays and you have to merge them. Now here is given a definition that how we can merge two arrays. So basically merge of two arrays results in an array C composed by successively taking the first element of either array and removing it. After this step, the element is appended to the back of C. So this is given the process. So we have to first find like how can we merge two arrays, and after merging the two arrays A and B, we have to merge it in such a way that the maximum length of all equal elements should be maximized. Okay, so let us see what we can do for this. Okay, so in problem B, you are given two arrays. Like let's say this is your array A. Okay, this uses array A, and then there is another array B, and both are of same length. Okay, now you have to merge them. So in merging, what will you do? You will form another array C. So now you will take either the first element of A or the first element of B and then append it. So let's say this was 4, 1, 2, 3, 6, 4, 4. This was 1, 2, 3, 4, 5, 6, 6, like this. So you will take either the first element of A or B. So let's say you take the first element of A, then let's say again A, then again A, 2. Then let's say after this you take first element of B, so 1. Then again let's say B, 2. Then again 3. So if you will form the merge of these arrays A and B, and after that all the equal elements, let's say this forms a continuous sequence of elements which are all of equal value. So you have to find the maximum length of this subarray which contains equal all the equal elements, all elements equal in the array C. Okay. So if you see that the process of merging, you will find that it will look something like this. If your A and B arrays are given, your C array will look something like this. That, yeah. Please unmute yourself if you don't have any doubts. So the C array will look something like this. First of all, it will consist some consecutive elements of A, okay, then some consecutive elements of B, okay, then again some consecutive elements of A, and then again some consecutive elements of B. Okay, so it will kind of alternate like this. First of all, you will write some consecutive elements from A here, then some consecutive elements from B here, then again from A, and then again from B. Okay, so like this. So if you want to maximize the total number of equal elements, what you will do, you will just break out your arrays A and B in chunks of consecutive elements, right? So if your array A is given like 2, 2, 3, 1, 3, 3, 3, 4, 4, so you will break it like this, your array A as this, such that all of these subarrays consist equal elements. Okay. Similarly, let us also break your array B like this. So let's say it consists these. Okay, right. So just break your arrays like this in chunks of consecutive equal elements, right? Now one thing you can obviously see is that uh, you can always combine two sequences which are from different arrays and consist of equal elements. So let's say you can always combine these two. Okay, how? First of all, what you can do, you just
Mute everyone.
please. Okay. Okay, sorry, I didn't saw the message. Okay, sorry. Okay, please unmute please everyone mute yourself if you don't have any doubts. It causes unnecessary disturbance. Okay, so what I'm saying is that you can always combine these two sequences, these two chunks of equal elements. How? So first of all, you can write these two. Okay, and no, don't write these two. First of all, write these ones together in the array C. Okay, after that write these two and then write these two. So in this way you can see you have basically merged these two into a single two in your array C. Okay, so the logic is that if you break your arrays A and B in sequences of equal elements, then you can never combine two chunks of equal elements from the same array. So let's say if your array consists of equal elements like this and your array B consists of equal elements like this. Okay, so if if this elements all are equal to X and these are also all equal to X, then you can never combine these two sequences of elements in your array C, right? The reason being that when you would be writing all these elements over here like X, 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 like this, okay, after that there will be some element Y in between them which will have to be placed, and after that only you can start writing this one. But in that case they are not combined because Y is coming in between these two X's, right. So you can never combine two sequences of equal elements from the same array. Okay, but on the other hand, you can always combine two sequences of equal elements from different arrays. So let's say this sequence of elements all contain X and this also all contains X. So the logic is that you can always combine these two in your array X, in your array C. Let's see how. So first of all, you will write all these elements. Okay, then you will write all these elements. Then you will write all these elements over here, followed by these elements over here. So in this way, you combine these two. So the total length will be, if the length of this is L1 and the length of this is L2, your total length will be L1 plus L2. Right. So all you need to do is
Hello.
that just iterate on which element all the elements should be equal to. Just iterate over the equal element. Let's say all the elements must be equal to some X. Okay. Then find what is the length of longest consecutive equal elements in A. Okay. What is the length of the longest subarray which consists of all x's? Let's call it L1. Similarly, in the array B, find what is the longest subarray which consists of all x's. Let's call it L2. So your answer will be L1 plus L2 if all the elements has to be equal to X in the final array C. So just iterate over all the possible x's, since A and B consist of all the elements from 1 to 2n. So just iterate X from 1 to 2n, then count how many, what is the longest consecutive length of sequence all consisting of X, and what is the longest length of subarray consisting of all X's in B. Just add their answer L1 and L2 and take maximum over all X's.
But it will be n square.
No, basically you will be using either a map or some count array. So that count array will be, we will be pre-calculating for A and B. Let's say count of two, let's say count one. Count one of two will store what is the longest length of consecutive equal elements equal to 2 in A. Okay, so let's say A consists of maximum of 5 length 2's. So count of 1 will be 5. Count 1 of 2 will be 5. Similarly, you will store for B what is the total maximum length of consecutive 2's. Let's say 6. So count 2 of 2 will be equal to 6. Okay, so corresponding to each X, just take maximum of whatever the user answer, comma, count 1 of 2 plus count 2 of 2.
Hello.
Yeah.
So can we do like that if we sort array A and array B and then we prepare an
No,
array
no, no, no.
C with
No, you
like
can't.
merging of two sorted array?
Merging of two sorted arrays. Okay, but
And then traversing the C array and storing the max count, max substring length of same digit.
so you can store what is the, so basically there, how will you will merge two sequences?
So
You can't
then it will
just
not be
arbitrarily merge them.
sub-array.
We cannot sort, no?
Yeah,
It
you
won't be
cannot sort
sub-array.
because, yeah, actually you cannot sort it because otherwise it will be, all array will be changed. Merge sequence will entirely change. You cannot sort it. Okay, so let's say if the array A consists of two elements, 3 and 2, such that 3 occurs before 2, then in the final array also, like this 3 should be coming before this 2. If you sort it, the order will be entirely changed.
Okay, got it, sir. Thank you.
Yeah. So just count, like for A, the longest consecutive all equal elements. So basically, let's say if this element is 3, keep on moving until you get 3's only, right? So let's say you get 5, this 5 number of 3's. So you will simply say count 1 of 3 is equal to maximum of count 1 of 3 comma 5. Okay, similarly, let's say you get 4 7 times. Similarly, find count 1 of 4 in the same way. Okay, what is the maximum length of subarray all consisting of ones in array A? Similarly, count 2 can be found, and then you just run a loop over X that finally what should all the elements equal to, and then maximize their sum. Okay, so let me show me my solution to it. So this is the solution. Like, first of all, we are taking just n, which is the size of the array A and B. Take A and B. Then I am declaring two arrays, count one for storing the equal elements length in array A and count two for in B. Then I just run a loop for I is equal to 0 to n. I fixed the this index. Then I start a loop from j is equal to I. So while aj is equal to ai, means these elements are equal, I increment my j. Okay, then count 1 of ai is equal to maximum of count 1 of ai comma j minus I, because this loop will break when aj will not be equal to ai. Okay, so overall there are j minus I equal elements with value equal to ai. So count 1 of ai is equal to maximum, I maximize it with this j minus I value, and then I set my I to be equal to j minus 1, because in the, so that in the next iteration I, when get incremented by 1, I move to the j value. Okay, if you don't do this, then actually same thing will be keep on repeating. Okay, that will be kind of O of n square. Same thing I did for the second array, that is B array. Okay, so again, while j is lesser than n and bj and bi are equal, keep on incrementing your j, and then find count 2 of bi. That will be maximum over j minus I. Same thing, and then at the end I iterate over x's, like what the final element should be all equal to. Then answer is maximum of answer, and count 1 of I and count 2 of I, and at the end print the answer.
Sir, but where did you check that longest subsequence of from both the arrays will be from the same character? Like two, there can be 4 2s and 3 2s also in two different arrays. So the longest subsequence is 4, but the characters are different.
No, you want the total, like the final subarray, final array which you are forming, like C. So in that case, you want all the elements to be equal. Like the subarray should be all consisting of equal elements. So you can't say that it consists of 2 as well as 3, because they are different. You cannot take their length.
Yes, that's what I am talking about.
Hmm.
मतलब अगर फर्स्ट एरे में लॉन्गेस्ट सबसीक्वेंस 2 का है और थर्ड सेकंड एरे में लॉन्गेस्ट सबसीक्वेंस 4 का है, और हम उन दोनों को सिर्फ ऐड करके करेंगे, तब तो वो तो आंसर गलत हो जाएगा ना.
No. We are finding what? We are not finding just longest sequence of continuous increase, longest sequence of all equal elements. We are finding longest sequence of all equal elements with value equal to ai, with value equal to I. So see, when I am maximizing count 1 of I plus count 2 of I, it means that the longest subarray all consisting of i's and longest subarray all consisting of i's in B. So when I am adding these two, like they all consist of only I. So they are all equal, na?
Yeah, I got it.
Okay. Any other doubts?
No, can you share this code in Discord, please?
Yeah, I will just share the pastebin link of it. Okay. Or maybe I can
Okay,
submit it after the testing is over.
okay, sure.
So that was the solution to B. Okay. And if there are no doubts, we can move to problem C. Okay. So problem C. So in this problem, you are given a list of n minus 1 edges, which is describing a tree of n vertices. And we have to decide to draw. Okay, so we have to draw the tree using this algorithm. Okay, so the first step is draw the first vertex, that is vertex 1. Then for every edge in the input, in the order, okay, so exactly in the same order in which you have been given the edge list, you have to iterate in the same order on the edges. If the edge connects an already drawn vertex u to an undrawn vertex v, we will draw the undrawn vertex v and the edge. And after checking every edge, go to step 2. What is step 2? Like if all the vertices are drawn, we terminate the algorithm. Otherwise, we again go to step 1. That is, we again check all the edges in the input list. And if the edge connects a drawn vertex to an undrawn vertex, then we draw that edge and draw the undrawn vertex. We have to find the number of readings. So readings is basically the number of times you have to perform step 1. So we have to find how many times we have to like perform this step 1. That is, we have to traverse this edges list. Okay. So let us see what we can do for this. Okay, so you are given a tree. Okay, so I hope everybody knows what a tree is. Okay, so tree is basically a graph, okay, which is connected and consists of n vertices and n minus 1 edges. Okay, so that definition of a tree. So you are given basically a tree like this. Okay, you are given all the edges of this tree. Okay, and you have to draw this tree. And what you do is that you first of all draw the very first vertex, that is vertex 1. Okay, so let's say this is vertex 1. Okay, after that you are given an edge list. Okay, so that edge list can be anything like this. Okay, let's say 5, 6, 7, 8. That edge list can be given in any arbitrary order. Maybe you are given this edge first, then this edge, then this edge, then this edge, then this edge, this edge, this edge. Okay, so the edge list can be given in any order, but it will consist of n minus 1 edges, which represent the tree. Now, after drawing the first vertex, what you do, you iterate through each of the edges in your edge list. Okay, let's say your edge list consists of 3, 4, then let's say 3, 2, 2, 5, 1, 2, 6, 8, 1, 8, and let's say 8, 7. Okay, so after drawing this one, you will iterate through this. So let's say 3, 4. So is 3 and 4 already drawn here? No, so you don't draw this edge. 3, 2, again no. 2, 5, no. 1, 2, you see 1 is already drawn here, so you will draw an edge from 1 to 2, and you will draw this 2 also. Again you move ahead. 6, 8, no. 6 and 8 are undrawn. 1, 8, yes, you can draw 1, 8 because 1 is already drawn, 8 is not drawn. 8, 7, yes, you can draw 8, 7 like this. Okay, so you can see after the first step 1, your tree will be formed like this. Now, as the tree is not complete, you will again repeat the same procedure. You will go through this edge list, again do the same thing. 3, 4, like 3 and 4 are undrawn. 3, 2, 2 is drawn, so you will like draw this 3, right? After that 2, 5, yes, you can draw 2, 5 because 2 is drawn, 5 is not drawn. 1, 2, okay, 1, 2 is already drawn. 6, 8, 8 is drawn, 6 is not drawn, so see you draw 6. Okay, then 1, 8, 1, 8 is already drawn, and 8 and 7 is already drawn. So as you can see, after this your complete tree formation is over. So you can notice that you performed 2 times step
Four
1
is
reading.
left. 4 is left.
Oh yeah, sorry, 4 is left. Right, 4 is left. 4 is left. Okay, so actually I didn't added 2, 4 in this edge list, that's why it was left. Okay, sorry, let's just add this at the end. 2, 4. So in that case 2, 4 will be drawn like this. Okay, 2, 4 will be drawn like this. So I think this 2 to 4 will be drawn in the first step only. Like, let's call t is equal to 1. Let's denote the number of times we have repeated step 1 by t. Okay, so t is equal to 1 means while doing the step 1 first time. T is equal to 2 means this node is drawn while doing the traversal for the second time. Okay, like this. So let us see what we can do for this. Okay, so if you notice, you will find that, okay, if you are given a tree like this, okay, so for root node, like node 1, node number 1, there is no issue because it will be drawn already. Okay, now all the vertices which are immediately connected to root node, let's say these are 2 and 3, they will definitely be drawn at t is equal to 1. This is clear, right? This will, they will definitely be drawn by t is equal to 1 or at t is equal to 1 because all these edges are coming in your edge list. Okay, now there is one more constraint. No constraint, like, okay, so by t is equal to 1 these will be drawn. Okay, next by t is equal to 2, like all these nodes will be drawn. Okay, so the observation here is that you can draw a node V. Okay, sorry. You can draw a node V if and only if you have drawn its parent. Okay, you can draw a node V if and only if you have drawn its parent. Okay, because see, we have drawn 2. Why? Because 1 was already drawn. We have drawn 3. Why? Because 1 was already drawn. Okay, so at t is equal to 0, the parent was drawn. That's why at t is equal to 1, when we would be traversing the list edge list, then when we would encounter this 1 2 edge, then 1 was already drawn, 2 was not drawn, so we draw 2. Then when we encounter 1 3, 3 was not drawn, 1 was drawn, so we draw 3. So that's why I said at t is equal to 1, all the vertices which will be connected to 1 will be drawn. Okay, and instead what I can generalize is that you can draw a node V if and only if its parent is drawn. Okay, the another thing you can observe here is that if your parent is drawn at time t, okay, then your child can be drawn either at t or at t plus 1. The reason is, let's say you have drawn this vertex at time t. Okay, so when you will be running the step 1 for t plus 1th time, then when you will encounter this hpv, then p has been drawn at time t, and at t plus 1 we are running the loop, we are running the iteration. So here v is not drawn, but p is drawn. So definitely at t plus 1 v will be drawn. Okay,
But
so
how at
if your
t only v can be drawn?
yeah,
If
I'm
you
explaining you,
okay.
so let's say if p is there, okay, and v is there, so let us examine the case when p and v can be drawn at the same time. Okay, so definitely first of all p will be drawn, right? After that only you can draw v. So let's say p was drawn at time t. Okay, let's say this edge is, let's say, p dash. So if the edge p dash p comes before the edge pv, okay, then definitely at time t when you will be traversing this, then you will draw this edge, you will draw this edge and draw this vertex p. After that, when you encounter this, you see that okay, p has been drawn earlier, so I will draw v. So you see v and p has been drawn both at the same time t. So this will occur only if this edge, that is the parent of p, that is p dash p, is occurring before pv.
Yeah, I got it.
Okay, so basically there are only two cases, like if this is the parent and this is the child, then uh, let's say the parent of p is p dash. Okay, so if the edge p dash p is coming before the edge pv, then in that case they will be drawn at the same time. Okay, otherwise they will be drawn at, like if p is drawn at t, then v will be drawn at t plus 1. So for denoting this, let's give an weight to this edge. So let's call this plus 0 if this condition holds. If this condition holds, then they will be drawn at the same time, so we give this edge a weight of 0 if this condition hold. If this condition does not hold, then in that case we give this edge a weight of plus 1. Okay, so if you form a weighted tree like this, okay, where each of the edges will have weight. So let's say this is plus 1, this is 0, this is plus 1, this is plus 1 plus 1, this is plus 1, this is plus 1. So in that case, in order to find okay that at what time this will be drawn, you just find the sum of weights of the edges on a simple path from root to this node. So like this will be drawn at time 2, this will be drawn at 1 plus 0, so this will be drawn at plus 1, this will be plus 2, this will be plus 2, this will be plus 1. Okay, so you know, now you know at what time each of the vertices will be drawn. Just take the maximum over them. Is this clear?
Can,
Or
can you please
yeah,
repeat this steps one again? Once again.
okay. So step 1 means the definition which has been given in the problem, or
No,
Like
last
at
step.
huh.
Last step.
Okay,
Last step.
okay. Last step means this one. A
The
No,
tree,
parent.
tree,
weighting of the
tree part.
edges.
Tree.
Oh, okay, this tree part.
Yes. How?
Yeah,
Okay,
yeah.
so see, let's see how we are forming this tree. Okay, that part is clear. Like if your current node is V, its parent is V, and the parent of parent is, let's say, P dash. Okay, so if this edge is coming before this edge, okay, the edge P dash is coming before the edge PV, then definitely this and this node will be like drawn at the same time. So if this is the case, we give this edge a weight of 0. Otherwise, we give this edge a weight of 1.
And what will be the weight of P dash P?
The weight of P dash P will again like depends on the parent of this P dash. Okay, and for the edges which are directly connected to 1, you can give them a weight of +1, because as I said you that all the vertices which are directly connected to 1, they will definitely be drawn at time instant 1. So you can give them a weight of +1, because this has been drawn at time t is equal to 0, and now I'm saying this has been they are all drawn at time t is equal to 1. So you can give them a weight of +1 for the edges which are directly connected to 1. Okay, and for the rest of them, like for edge VP, find the parent of P, let's call it P dash. Check if this edge is coming before this edge. If it is so, then give a weight of 0, otherwise 1. Because 1 means what? Like if this is T, this will be T plus 1. Otherwise, 0 means TT. Okay, so I can show you the code. Okay, if still there exist doubts, you can ask definitely.
So okay, I got the part that we have to put either 0 or 1 for each
Hmm.
row. No, that's for
Yes,
each age.
yeah, for each edge you put a weight of either 0 or 1 depending on whether the parent and the child will be drawn at the same time or at different times.
Means we have to check whether it is coming at the
uh,
before or after. That's it.
yes, same thing. So see, the implementation is here. Like we are first of all taking the size of this tree, and then I am declared a parent array to denote what is the parent of vertex V. Since the tree is rooted at vertex 1, so each node will have a unique parent except for one whose parent will be -1. So I take the edges UV, and then I am also storing that at what position this edge is occurring in the edge list. Okay, so the position of UV, or you can say VU, is I. Okay, so I'm mapping it in a map. Then I am also forming this adjacency list. Then I'm running a DFS from the root, that is 1. Okay, so the DFS looks like this, that I am passing the current vertex, what is the parent of this vertex, adjacency list, and this parent list. So I set the parent of S to be equal to parent, and then I iterate for every node which is adjacent to S. So if this is not parent, if this is parent, I continue. Otherwise, I run a DFS from E. The parent will be now S, and the other parameters will remain as it is. So I hope this DFS is clear. This is basically for finding the parent of each node, right? Now, once this DFS is done, we have the parent of all the nodes. Then what we do, we just iterate over all the nodes from 1 to n. So if the parent of a node is 1, so in that case, we know that the weight of the edge connecting I and Pi will be 1, right? So that's why weight of I comma Pi and Pi comma I is 1. So I am using another map of pair. Okay, so this weight will denote the weight of each edge. Okay, so this was for all the vertices which are directly connected to 1. I am setting the weight of them. Otherwise, if it is not the case, then pi will be strictly greater than 1. Pi cannot be -1 because -1 means that it is the root. Root has parent -1, so it has no edge, so no meaning. So if pi is greater than 1, so in that case I am storing three things: u, v, and w. So u is like the current node, v is the parent of current node, and w is the parent of node. So this is w is same as p dash. Okay, then I'm checking if mapping of VU is greater than mapping of WV. So what does mapping denotes? Mapping is like at what position this edge is occurring. So this is same as the condition what which I was telling you, that if PP dash is uh, coming before PV. Okay, so this is same like this. So if this is the case, then I am setting the weight to be 0. Otherwise, I set the weight of UV to be equal to 1. And then I run another DFS, call it DFS2. So let's see how we are running DFS2. So in DFS2, we have the current node, the parent of this node, adjacency list, the weight of each of the edges, then answer. Answer is basically the maximum distance of any node from the root. And then this is current. Current denotes what is the sum of all the weights up to S from root. Okay, so answer is maximum of answer comma current. Then I iterate over each of the adjacent nodes. If E is equal to parent, so I continue. Otherwise, I run a DFS from E, then parent will be S. So, and you see this one, current plus weight of SE. Basically, if the sum of weights of on all the edges from root to S is current, then the weight of all the edges on the path from root to E will be current plus whatever is the weight of S to E. Okay, and at the end, I just print the answer.
Yes, okay. What was the case for the first TFS? Means for what we are running that TFS, first one? What
So
was the
we
task?
are running the we are running the first TFS to basically find the parent of each node. So you see, when I'm running this DFS, if you see this DFS, we are doing nothing special, just setting what is the parent of node S. Okay, so initially you see I am passing -1 because the parent of 1 will be equal to -1. And then when I'm running this DFS from its child node, I am passing S because you are going from S to E. So the parent of E will be S. Okay, and we are passing this array to store permanently what is the parent of each node.
Okay.
Okay, so I hope this was clear to everyone, or do anyone still have any doubts?
DFS2, why?
Okay, so see, oh sorry. So in DFS2, so see why we are running DFS2. See, if you see this, see if you see this, you will find that we have to basically find the time at which each of the nodes will be drawn. And that would be, for example, if you want to find at what time this node will be drawn, you have to find the sum of all the weights of the edges which are encountered in a path from one to this one. Okay, so like +1, and then here it is 0. So +1 plus 0 is equal to +1. So this node will be drawn at +1. Similarly, in order to find at what time this will be drawn, you have to find the sum of these edges which are lying on the path from 1 to 2, 1 to this node. So +1 plus 2. So what I'm in DFS2, what I'm saying is that, so I am running a DFS2 from this node. Okay, let's say V. So here I am passing at what node I am, what is the parent of this node. Okay, I am passing that adjacency list I am passing, and then I am passing what is the sum of all the edges in the path from one to this, that is stored as current. Okay, and then I'm also passing an answer. Okay, and I am passing this answer by reference. So answer will store the maximum total distance from one to each of the nodes. Okay, so that's why in the very first step I am maximizing this answer as max of answer comma current. Okay, so current is the total sum of the paths sum of the weights of the edges on the path from 1 to V. Okay, now when you move, so let's call it S rather. So when you move from S to E, so what will be the new total distance? That will be nothing but whatever is current plus whatever is the weight of this edge, weight of the edge S to E. Okay, that will be called in DFS2. When you will be running from S, E, the parent will be S. Okay.
And that only basically denotes the time. Means,
Yeah, that denotes the time. That denotes the time. So that's why you see we are doing this. That in DFS2, we are running from E past parent will be S, and then the time up to this point will be current plus weight of SE. Okay, and see we are passing here answer by reference so that no copy of answer is obtained, and so that whatever is the final answer that is stored in this answer. Okay, otherwise copy of answer will be sent to this DFS call and answer will be 0 at the end. Finally, we want answer to be updated at each time the recursion is called. So that's why we're passing answer by
so the
reference.
time complexity is linear.
Yeah, the time complexity, no, not linear, but n log n, because see we are also like calling weight of this edge. So this is a map now. Map takes logarithmic time. So n log n you can say.
Okay.
Okay. So let us now move to the next problem, which was problem D. So this is the last problem. So in this problem is very small and very simple. You are given two arrays A and B, both of length n, and your task is to count the number of pairs I and j such that I is lesser than j, and ai dot aj is equal to bi plus bj. Okay. And the constraints are given n up to 2 into 10 to the power 5, and ai and bi both are in the range 1 to n. So this is a very you can say very good constraint. Like without this it might not be possible to solve it. Okay, so let us see how we can do this. Okay, so let me formally restate the problem. So basically you are given two arrays A and B. Okay, so you are given two arrays A and B. Okay, you have to find the number of pairs I and j such that ai multiplied by aj should be equal to bi plus bj, right? And it's given that all of these elements lie in the range 1 to n. Okay, so the elements lie in the range 1 to n. Okay, so let's see what we can do for this. Okay, and it's given I is lesser than j. So this basically means that you should not count the same pair twice. So means that 2 3 is same as 3 2. Okay, that's it. So let's see what we can do this. So see, you are given ai into aj is equal to bi plus bj, right? So what can be the maximum value of bi plus bj? That will definitely be lesser than or equal to twice of n. Okay, so what? So it means that ai into aj will always be lesser than or equal to twice of n. Okay, now if this is the case, then you can definitely say one of these, that is either ai or aj, must be lesser than or equal to square root of 2n. So either this should hold or this should hold. Is it clear?
Yes.
Hello. Yeah, so either this should hold or this should hold, right? So so we divide our searching in two parts. Okay, the first part
But
consists of count.
this
Yeah,
will be possible when AI and AJ are equal. No?
yeah, like if ai and aj are equal, then this will hold. Like ai will also be equal to square root of 2n. Okay, 1 minute. See, like if ai into aj is lesser than or equal to 2n, then definitely this or this will hold true. Either ai will be lesser than this or aj will lesser than this, because otherwise what will happen, ai will also be greater than square root of 2n, and aj will also be greater than square root of 2n. So if you multiply ai and aj, they will become greater than 2n, but obviously this is contradicting this. So that's why I told, if this is the case, then either this will be true or this will be true. That is, one of ai or aj must be lesser than or equal to square root of 2n. I hope this is
Either
clear.
I I guess
Yeah.
both of them should be true. Then
No,
their
no,
product will
no.
be.
No, both of them can't be like, not necessarily it's true. Let's say if your value of 2n, let's say, is equal to 6. Okay. So if your
Mhm.
AI is equal to 1 and AJ is equal to 6. So although 1 into 6 like is lesser than or equal to 6, but is 6 lesser than or equal to square root of uh, 6? No, no.
No,
But
no,
1 is
no.
definitely lesser than this.
Mhm. I got it.
Okay. So I can see some chats. Okay. Okay. So I hope this point, up to this point, is clear that if AI into AJ is lesser than or equal to 2n, then either AI will be lesser than square root of 2n or AJ will be lesser than or equal to square root of 2n. Okay. So we divide our searching or counting in two parts. The first part consists of counting those pairs IJ such that AI is not equal to AJ. Okay, we will first of all count those pairs ij. Okay, so if AI is not equal to AJ, without loss of generality, let's assume AI is strictly greater than AJ, because definitely if AI and AJ are not equal, one of them would be strictly greater than the other, right? So let's say AI is strictly greater than AJ, right? So in that case, we can definitely say AJ will be lesser than or equal to square root of 2n, right? This part is clear, like up to this part. So we are dividing the counting of pairs ij in two parts. So I am first dealing with part one. So in part one, we are assuming that ij pairs are such that AI and AJ are not equal. So in that case, let's say AI is greater than AJ. So in that case, AJ will be lesser than or equal to square root of 2n, right? So what we will do, we will fix each of the AI. So we fix each AI. So we fix each I instead. So fixing I will fix AI. Okay. Then we iterate over all the values of AJ, right? So the values of AJ will be around order of square root of 2n. So we will iterate for each possible AJ from 1 to square root of 2n. Okay. So if your AI and AJ are fixed, then AI into AI into AJ has to be equal to BI plus BJ. So your BJ will be AI into AJ minus BI. Okay. So once you fixed your AI, your BJ will be this much. Okay. Once you fixed your AI and AJ, your BJ has to be this much. So you simply add what is the of count of uh, AJ and BJ. So AJ is what we fixed and BJ will be this much. AI into AJ minus BI. So initially what we will do, we will store the count of each of AI and BI pairs. Okay. So we will store how many these pairs are occurring, okay, in some count mapping like that. Okay. Now we are fixing the AI, we are fixing I, and then we are iterating for each value of AJ from 1 to square root of 2n. Okay. Once you fixed AI and AJ, you calculate the BJ value and then count how many edges, or you can say how many these pairs are equal to AJ and this thing. Basically, you count how many AJ BJs are there.
Hello.
Yeah.
Sorry, but I'm not getting from the last three steps.
Uh, so
Three steps.
part one.
There, yeah, it's clear. Part one is clear. Yeah,
Okay.
three steps. Last three steps.
See, what I am saying is that you know that if AI is not equal to AJ, then let's say AI is greater than AJ. So in that case, AJ will be coming out to be lesser than or equal to square root of 2n, right?
Yes.
So now what we are doing is that we are fixing each I. Okay, so let's say we fix this I. Okay, so if you fix this I, it will be having some AI and BI, right? So now you iterate over all the possible values of AJ. Now you know that there are only these many values of AJ. So you iterate over the values of AJ from 1 to square root of 2n. Okay, so you iterate over the values of AJ from 1 to square root of 2n. So if AI and AJ both are fixed, then BJ is also fixed. How? Because you have to make this constraint AI into AJ should be equal to BI plus BJ. So what is the value of BJ? BJ is nothing but AI into AJ minus BI. So since you have fixed all of these, your BJ is also fixed. So now corresponding to this AI BI, what is the total count of AJ BJ? That's why we are adding this count of AJ and BJ, which is given by this formula. So that is the second value of this. So you add this to your answer.
And you told previously to store the value of every pair in the
Hmm.
map. So it will
Hmm.
basically take n square time. You told
No,
here
no,
AI,
no. We are
BI.
so AI BI na. So there are n elements in total. So you will iterate for I is equal to 1 to n and just say count of AI BI plus plus. So this is O of n, not O n square.
Okay.
Okay. So this part is clear, right? How we are counting this, right? Okay.
Yeah, it's
So
clear.
this is for part one. When AI is not equal to AJ, then we basically fix each I, then we iterate over all the values of AJ from 1 to square root of 2n, then we find the corresponding value of BJ and just add the count of AJ BJ, and BJ is given by this formula. Okay, so this will take you, the time complexity of this will be, there will be n indices for I, and for each of them you will fix the value of AJ, so there will be square root of 2n values, right? So it should ideally be this, but since you are using here a mapping, it will be n into square root of 2n and then again a log factor of n. Okay, so
Yes.
this is the time complexity for calculating the first part where the indices are like this. Okay, so although this will give you TLE, I will tell you how you can actually like remove these log factor. Okay, but let's wrap this calculating part 2 first. Okay, so in part 2 we are calculating those indices I and j such that AI is equal to AJ. Okay, we are considering only those indices. So if AI and AJ are equal, let's say they are equal to x, so the constraint is AI into AJ should be equal to BI plus BJ, but both of these are x, so it becomes x square. So x square is equal to BI plus BJ, right? So what we do here is that we just iterate over x. Okay, we just iterate over x, and let's say this is x, this was, let's say, b1, then x b2, then x b3. So corresponding to each pair AI BI such that AI is equal to x, we collect these b values. Okay, so that will be in a form of array like b1 b2 b3, and then we find how many pairs of elements you can choose from this array such that their sum is equal to x square. Now this is a very standard problem that you are given an array and you have to count how many pairs of elements when added together gives a target value. This is a very standard problem, right? So that you can solve in order of, like, if n is the size of array, so you can solve in order of n log n.
Or
You can
linear also.
count.
We can
Yeah, actually, yeah, if it is sorted, you can do linear also, but using map also you can do this. Okay, there is no issue. So you can do that in order of n log n. So that's it for part 2. What you do, like, you iterate through array A, and you store like a map of int comma vector of int. Okay, so like what you will do for this x, you will say mapping of x dot pushback b1. Okay, pushback b1. Similarly, mapping of x pushback b2. So basically, mapping of x will be a vector which will consist of all these b1 b2 b3 like that. Okay, so you just iterate through your map. Okay, iterate over the first element of the map, that will be like x. Once your x is fixed, you get, okay, corresponding to this x as AI, what are BI values? Okay, then you just find the number of pairs such that their sum is equal to x square. Okay, and add it to your answer. Okay, so that is for part 2, how we can calculate part 2. So the calculation of part 2 will take you no more than O of n log n time. Okay, so the only hectic part is removing this log n from the first part. Okay, so if you see the very first part, let me first show me my solution, then I can tell you how I optimized it. So let's see my solution. Okay, where did it go? Okay, it's division 2. Think. Okay, so let's first see this solution. So this is very simple. Like I am taking A and B. Okay, that's simple. Then I am storing the count of AI and BI in a mapping called MP. So MP of AI BI plus plus. Then I am storing for each AI value what are the associated BI values in a form of a vector. So this MPP is a map of LL and vector of LL, basically long log. So MPP of AI dot push back BI. Okay. After that, this is calculation of part 1. So here what I am doing, I am fixing the first index AI, then I'm iterating on the AJ values. So AJ will vary from 1 to square root of 2n. So this is same as AJ into AJ is lesser than or equal to 2n, means AJ is lesser than or equal to square root of 2n. Then I'm checking this condition that AJ should be lesser than AI. If this is the case, I just add the value of AJ, and this is BJ. BJ will be nothing but AI into AJ minus BI. So this was for part 1. For part 2, I just iterate over each of my map, like each of the possible values of X. And then I store, okay, what will be AI? AI will be E dot first. And then what will be the associated BI values corresponding to this AI? That will be E dot second. Then I declare a temp mapping. Then I iterate over each of the elements of the vector V, and I add temp of AI into AI minus each. Why this? Because you want the total sum to be AI square, and the current element you are taking is each. So previously you should have got AI square minus each. So what is the total count of this much? That has been encountered previously. I add it to my answer, and then temp of each plus plus. Okay, so this was giving me actually TLE because of this part. So this part is basically n into square root of 2n into log of n. So for optimizing this, what I did is that I fixed my AJ value. Okay, so let me show you how I optimized it. So earlier what we are doing for part 1, we are fixing the I value that due to which AI was fixed. After that, we are iterating over AJ from 1 to square root of 2n. We were then calculating BJ, and then we are finding how many AJ BJs are there. Okay, we just added the count of that. So now what we are doing, we are just changing the order of loop. We will now run the loop of J first. So first of all, we will run a loop for AJ. So AJ will vary from 1 to square root of 2n, right? Then what we are doing, we are calculating the count of those B values whose AI is equal to this AJ, right? So if you see the see here, uh, so in my second solution, which was the accepted one, I am just changing the order of loop. So here I am first fixing the AJ values. So AJ will run from 1 to 2n. Then I am declaring a count array of size n plus 1. Then I iterate over all the AI BI values, and if AI is equal to this AJ, because I have fixed AJ, so I will consider only those AI BI for which AI is equal to this AJ. If this is so, I increment the value of BI. Okay, so after doing this, I again iterate over all the AI values, fixing the AI. If AJ is lesser than AI, then I just simply add the count of AI into AJ minus BI. Okay, so in the earlier case, we were maintaining in terms of pairs, like count of AI BI. But now that was giving us an extra cost of log, because map of pairs, because pairs count can only be maintained in a map. But now since we are fixing AJ, so now here we have to just count the pairs, count the number of BI values whose AI is same as AJ. Okay, so that's why now map is replaced by a linear array called count. Okay, so if this is basically BJ, if BJ is within 0 to n, so you add the count of this. And part 2 is same as the previous one, so there is no change in this.
Can you explain why you are maintaining the count of AI? Like, what is this AI equal to AJ? Like, I don't.
Okay, sure. So see,
What is this underscore and difference?
yes, I'm telling. So I am basically using a variable a underscore j to denote AJ simply. Okay, so this is the first thing. A underscore j I am just using as a variable name. This is same as AJ. Okay, so part 1 was clear, right? When I earlier explained you the first solution, that was clear, or was there any problem there when I was
No, that is
explaining
clear.
this? That is clear. Okay, fine.
Yeah.
So if that is clear, then this should also be clear, because see, in the first part we are first fixing I, due to which AI was fixed. After that we were running a loop over AJ from 1 to square root of 2n, right? Then we were evaluating BJ. BJ was what? AI into AJ minus BI,
Yes.
right? So in the second optimization, what we are doing, we are not running a loop over I first, we are running a loop over AJ first. The outermost loop is over AJ, so AJ will run over 1 to square root of 2n, right? Then we are running a loop for I is equal to 0 to n, right? So now AI is fixed, AJ is fixed, so what will be your BI will be nothing but AI into AJ minus BI, right?
BJ.
So you will try to,
BJ.
yeah, this is BJ, this is I.
Yeah. Yeah. Yeah.
So you will try to add how many AJ and BJ are occurring in your array, right?
Yes.
So for earlier we were maintaining this in map, but see,
Mm.
since we have fixed this AJ, we can declare a temporary count array like this, count of size n plus 1, and then we can simply remove this AJ from here and simply say count of BJ. Okay, and here we will run another loop where we will increment the count of BI by 1 if and only if corresponding AI value is equal to AJ.
BI would be there, no?
Where?
Instead of AJ.
Here.
No, in the like when we are counting the pairs.
Here you mean?
Yeah. Yeah.
No. See, uh, see, before using this count array, we were using a map array, right? So map.
Got it. Got
So
it. So count of BJ is like count basically AJ corresponding to BJ, right?
yes.
Okay.
So
Okay.
this count is only corresponding to those AI VI for which AI is equal to AJ.
Okay.
Okay, so now you can directly use count of BJ instead of saying AJ BJ, because count of BJ definitely means that AI value must have been equal to AJ. Then only we are incrementing this BI value, you see.
Yes.
So you see here that when we are running this loop, so first of all we are updating this count value, right? So only if AI and AI is equal to AJ, then only we are incrementing the count of BI. Okay, so if count of certain BI is equal to 2, it means there are two values of AI BI such that AI is equal to AJ and BI is equal to that BI. Okay, so that's why here we are directly adding the count of BJ. This is nothing but BJ. Okay, and it is understood that AJ must be equal, AI for this must be equal to AJ, because then only
And
we are incrementing.
are we sorting any array beforehand? Are we?
No, we are not sorting. I don't think we are not sorting it, right? because if you sort it, then like it won't change the answer, but there is no need of sorting, like it won't change the answer.
Okay.
Okay, so is there any other doubts?
Can you share the submission once into the chat?
Yes, I will share the submission link in the chat as well. Okay, like other than this, if you have any doubt, you can ask.
What is this hacking part in these code forces? I don't understand. Here it is given
See,
open and
yeah, basically what happens is that when you are given a contest, so it only runs on certain test cases, let's say 10 or maybe 12 test cases. That's why you would be seeing pre-test passed. So pre-test is certain bunch of test cases which are not total but just a part of total test cases. They are very few. Okay, so in hacking phase you can actually claim that some solution is giving wrong answer by giving some certain test cases. For example, if you feel that although my solution is correct, but you feel that on a certain input it won't give you the right answer, then you can actually hack my solution using that test case. And if it is actually giving, my solution is actually giving wrong answer, then after the system testing or like hacking phase is over, I will be shown hacked, my solution has been hacked. Okay, and
so
that your
so
test case
do
would be
they
added.
okay? So do they give only 10 to 12 test cases only in the
Yeah,
pre-test?
in pre-test they don't give very large all the test cases because otherwise their system will hang. So that's why they just give you selected test cases such that if your solution passes those test cases, it can be said that it will probably pass all the test cases. In most
Okay.
cases pre-tests are strong, but sometimes if weak pre-tests are given, then it might be possible that after your your system testing is over, you are showing a wrong answer.
Okay.
Sir, if AI is varying till end and AJ varying till end, so their product will be n square.
Okay, what, can you repeat?
AI is varying till n and AJ also n. So
It wait to n. It's not pairing
Yeah,
till n.
so if AI and AJ both are varying from 1 to 1, so that's already given, right? So that's why I'm saying that if AI, like BI and BJ, they are also varying from 1 to n. So AI into AJ will definitely be lesser than or equal to 2n. So definitely one of them will be lesser than or equal to square root of 2n. Like otherwise I showed you, like proved through contradiction also, that it can't be that both of them are strictly greater than square root of 2n. Like one of them has to be. So in part 1 I am assuming that, let's say AI is not equal to AJ. So in that case let's assume that AI is greater than AJ. So if AI is greater than AJ, then definitely AJ must be lesser than or equal to square root of 2n, because this is a smaller one, right? So that's why I'm iterating over AJ from 1 to square root of 2n.
in the first equation, the RHS is 2n, but not n square y.
I don't understood. Yeah, this one.
Yeah.
So see, if AI and AJ, like in the worst case, what can happen? Both can become equal, right? So if both of them become equal, it becomes like x square is equal to 2n. So in that case, it comes like square root of 2n, right? So that's why either AI should be lesser than this thing, or AJ should be lesser than this thing.
Yeah, got it.